I want to spend a little bit of time looking at the starter code and considering how we can approach the problem of trying to get our robot here, over to our destination, way back over there. So here's our robot, and I have the starter code loaded up, or the demo simulation loaded up. And let's take a quick look at our starter code for the control program. So our starter code for the control program is a little bit simpler than the starter code that we had for homework 1. Specifically, the handling of, well, a couple changes. First thing, the handling of determining when we've gotten to the goal is now rolled into the robot class. And then the other thing that we have is we've significantly reduced our interface that we have between like what the robot provides and what the robot's able to do. So we really only have 2 sensors, and both sensors are a single floating point number. So we have this range sensor that tells us how close the nearest forward obstacle is. And then we have a rotation sensor that's going to tell us what angle the robot's at. So the other one is a robot. Let's go look at the robot thing in robot.hh. Our other thing is position underscore t. So that's the like theta of the robot's position. And the robot interface no longer exposes position X or position Y. That's not public information, or not a sensor that you have for this assignment. Similarly, you don't directly have access to our laser scan anymore. All you get is this one range floating point value. So working with the 2 sensors, the angle sensor and the range sensor, we can then do one thing, which is to set our velocity. But that means that we may want to build up some state to be able to figure out how to make it through the maze here. But let's go ahead and start this existing control program, which does some stuff with range. It doesn't even look at its angle, and see what it does. So we run brain, and it's going to print out a bunch of stuff about how it's setting the velocity, and now the robot is turning. And previously we had 2 different commands for robot motion. We had robot sort of turn angle for the wheels, and then we had robot velocity, which was a forward-backward velocity. Here, instead of having car steering, this robot's trying to do skid steering or tank steering, where we have separate control over the wheels on the left side and the wheels on the right side. And so conceptually, the way we turn is if we make the wheels on one side go faster than the wheels on the other, we can be moving forward. One side goes faster, and we turn away from the side that's going faster. In practice, the simulation physics are awful. So the things that actually work on this simulation robot, and it's not that Gazebo is especially awful, it's just that the robot that I built is bad. But the actual behavior that we get is that we can reliably turn in place if we set the velocity with one wheel, one side to be a speed, and then the velocity of the other side to be exactly the same speed negative. The robot will rotate in place. And then we can reliably go forward, but doing sort of turning and going forward is not great with this particular robot setup. That's something that I hope to fix in future starter code, but it's fine for this assignment. We don't need to be able to turn and go forward at the same time to solve a maze. We can turn in place and then go forward. But what we have is, what this thing was trying to do is it's trying to be a wall follow. But what it actually does is just get stuck on corners. So the first thing that I guess I want to fix is I want to fix the behavior that causes it to get stuck on corners. So the reason it's getting stuck on a corner is that the logic that it follows is if there's an obstacle directly in front of it, it's going to turn left. If there's an obstacle between directly in front of it and 1.7 meters, so not directly in front of it, but there's still an obstacle, then it goes straight, and it's doing that to try to catch the wall. And otherwise, it's going to turn right. But what it's gotten into this position of is there's the corner of the wall that is close enough that it counts as a close obstacle, but no matter where we turn, the options are either that we see the wall close to us or we see nothing. And so this strategy in the starter code doesn't work at all. So instead of making it so that when we see an obstacle, we're going to go forward, we're going to go forward if we see no obstacle. And yeah, we're going to try this. So if there is an obstacle, we turn left. If there's no obstacle, we go forward. Let's see what we get with that. So I have to rebuild this thing. This robot's just sitting here turning. It's not super important where it starts. We don't necessarily need to have it start at the start point for this to be a useful test. So we run the control program, and the robot's going to move forward until it hits this this wall here. And then once it gets close enough to the wall that it doesn't like it, it should turn left. And then, so what this laser is trying to do is simulate a sonar, because that's what we have on the physical robot kits. But what we have doesn't work quite exactly the same as a sonar, because we're taking the minimum of these lasers, and depending on the angle, the minimum of these lasers. So we can hit a position where we are closer, sort of direct distance from the sensor, like straight line distance from the sensor to where the hit is, because we're doing this longer angle. And so it's going to see objects that are close to it on the sides as being closer than objects that are directly in front of it, which is true, but I don't know how closely that's going to resemble the behavior that we have on the physical robots. Actually, if the TA is working on trying to understand what the physical robots do and trying to build a better simulation of that, but we don't need that yet for this particular assignment. So this logic that we have here of going to a fixed distance, so the distance is if we're less than a meter we turn, otherwise we go straight, is causing it to hold a fixed distance sideways from the wall because of this angle behavior. And then when we eventually hit another wall, we're going to turn. And so we follow walls when we have sort of convex turns here. But we have a slight problem. And that slight problem is that when we have a sharp corner like this one, the robot ends up being unable to detect the difference between having reached the optimal distance from a wall and not. So here it is just going along straight, even though if we were doing a clean wall follow, it would have turned into that doorway. Now, I don't think that we end up being close enough for it to fix it with a turn here. No, it was sort of perfectly lined up so that it was running parallel with that wall. So this robot's just going to keep driving around in a circle and never go through any of these doors. So the next step here would be to try to detect the case where we hit a doorway, and then decide whether we want to drive through the doorway or not. And once we get into having a doorway detector, that ends up actually being sort of neat for trying to do mapping, because we can keep track of whether or not we went through doorways. We also have angle information, so we can keep track of which direction we're going through the doorway. So going through a doorway sort of towards the goal is the same direction we started facing in, can be meaningfully different in our control program than going through a doorway away from the goal. I don't think there's a stateless solution to this class of maps. I think our robot's going to have some state, but figuring out what that state is, how to do the data representation, and how to work with this very limited set of sensors in order to build up a state representation is it is the puzzle for this assignment. You can build an abstract graph map that sort of treats this as being a set of hallways where the hallways are connected by doors, and even takes into account these sort of middle walls. But you may not have to. So however you manage to solve this is a reasonable solution for the assignment.